Power system stability sounds complex, and it is. But in this series, I'm going to break it down one concept at a time. Before we jump into power system stability or any kind of system stability, we first need to define a few core ideas about how we describe a system state. First, state variables are the smallest set of variables needed to fully describe the behavior of a system. In a power system, this could include the rotor's rotational speed and its angle. A collection of these variables forms what's called the state vector. The system state refers to the values of these variables at a specific moment in time. For example, a rotor might be spinning at 5 radians per second and sitting at an angle of 35 degrees relative to the stator field's electrical angle. That's the system state, say at time t equal 5 seconds, for example. The state space is the coordinate space formed by the state variables. Each point in this space represents a unique system state. And finally, the system trajectory is the path traced over time as the system moves through the state space. So, if you move from one system state S1 to another S2, the trajectory is the series of states connecting them. Alright, now that we have those definitions, what does it mean for a system to be stable? Let's pick a random state variable and observe how it behaves over time. Suppose we start from some initial condition. The resultant system trajectory shows how the system evolves. Now, imagine a small region eta around that starting point. If every possible initial state inside eta leads to a trajectory that remains within a bounded envelope over time, the system is said to be stable. But if even one trajectory escapes any bounded region, then the system is unstable. Now, this definition applies to any type of trajectory, including one that doesn't move, a single point trajectory, where the state variables remain constant. This is called an equilibrium point. Again, let's start somewhere in a random area around this equilibrium point. The system would be stable at this equilibrium point if the new trajectory stayed within a finite area around the equilibrium point. But if they drift far away, the equilibrium is unstable. Just because a system is at an equilibrium point doesn't mean it's stable. The state variables may not be changing, but when disturbed, the system might still become unstable. Here's a simple analogy. Imagine a ball resting on a hill. In one case, the ball is nestled at the bottom of the hill. In another, it's perfectly balanced at the top. In both cases, the ball isn't moving. So, both are equilibrium points. The state variables in this case are the horizontal position and speed. This is the minimum set of variables we need to describe and predict the system's behavior. In both cases, the derivatives of state variables are zero. But disturb the ball at the bottom and it rolls back. That's a stable equilibrium. Disturb the ball at the top and it rolls away. That's an unstable equilibrium. Good, I think we have enough now to start talking about power system. A power system is a highly nonlinear and complex system. So, analyzing the entire state vector at once would be incredibly hard and computationally expensive. So instead, we split the problem into parts by studying frequency, voltage, and rotor angle stability separately. For linear systems, if stability holds under small disturbances, it usually holds for large ones too. But that's not the case with nonlinear systems. So, for power systems, we examine both small and large disturbances. In this video, we'll focus on frequency stability. The frequency of the voltage is a global variable. It stays the same across the entire power grid. This frequency is tied directly to the speed at which synchronous machine rotors are spinning. As we saw earlier, to assess stability, we need to understand how frequency changes over time. To do that, we'll zoom in on the rotor of a synchronous machine inside a power plant. This rotor is driven by a turbine and magnetically linked to a stator. It starts off rotating at some synchronous speed, either 50 or 60 Hz, depending on the system. The turbine provides mechanical power, which is converted into electrical power by the generator. Let's now apply the law of energy conservation to the rotating mass of the rotor. The input mechanical energy equals the output electrical energy plus what's stored as kinetic energy in the rotor. That means the stored kinetic energy is the difference between the input and the output power. Kinetic energy in the rotor is given by 1/2 times moment of inertia times rotational speed squared. The moment of inertia reflects how much mass is in the rotor and how that mass is distributed around its axis. At the same speed, a heavier rotor with mass further away from its axis stores more kinetic energy. Now let's take the derivative of both sides. On one side, we get the rate of change of omega squared, and on the other, the derivatives of mechanical and electrical energies, which are just powers. But what we really want is the derivative of omega, the rotation speed, because it's directly linked to the frequency variations. To simplify, we linearize omega squared around the synchronous speed using Taylor expansion and keep just the first order term. Taking the derivative again gives us the derivative of omega, which is what we're looking for. Now we substitute back into our equation. At this point, we already have a neat expression. The rate of change of rotational speed depends on the difference between mechanical and electrical power. But instead of using inertia and speed separately, power system engineers often use the inertia constant, h, to normalize inertia and simplify equations. This constant is equal to the kinetic energy stored in the rotor at synchronous speed divided by the rated power. We also express speed in terms of frequency using the formula omega equal 2 pi times frequency. Putting it all together, we get a beautiful result. The change in frequency is proportional to the power imbalance and inversely proportional to the system's inertia. This is known as the swing equation. It's deceptively simple, but incredibly important. The swing equation describes how a synchronous machine's rotor speeds up or slows down when there is an imbalance between the input and the output power. Think of it as the rotational version of Newton's second law. From this equation, we get three scenarios. First, if mechanical power is greater than electrical power, frequency increases. The rotor speeds up. Why? Because the extra energy gets stored as kinetic energy. Second scenario, if electrical power is greater than mechanical power, frequency decreases. The rotor slows down. That's because kinetic energy is being pulled from the rotor. And lastly, if mechanical power is equal to electrical power, the rotor spins at a constant speed. That's an equilibrium point. Here's a simple analogy to help visualize this. Picture a water tank being filled from the top by a pump and drained at the bottom through a valve. The water level represents the frequency. Pump's flow is like mechanical power input. The valve's flow is like electrical power output. If the pump brings in more than what the valves lets out, the water level rises. If it brings in less, the level drops. If input equals output, the level stays constant. Small disturbances could be tiny changes in the valve's flow. Large disturbances might be a sudden pump failure. In the size of the tank, well, that's like the system's inertia. The bigger the tank, the slower the level changes when flows are imbalanced. That's it for today. In the next video, we'll dive deeper into frequency stability during small and large disturbances using the swing equation as our guide. Thanks for watching. Don't forget to like, subscribe, and let me know what you think of this format compared to the Manim animations.